fluid operation classroom. Today we are going to discuss growth of laminar boundary layer over a flat plate. My name is Shekhar Bhattacharjee. Let us first read out the problem. It says, consider a two-dimensional steady laminar flow of an incompressible fluid, let's say water, with zero pressure gradient. We'll see what is zero pressure gradient over a thin horizontal flat plate of length 2 meter. So basically, this is my two-dimensional flow here, and here's my flat plate here, and this is length is 2 meter. Free stream velocity is 1 meter per second. So this is my free stream velocity. This is my free stream velocity, and this is a flat plate. So of course there is a boundary layer forms over this flat plate due to momentum diffusivity. A boundary layer thickness of 1 mm is observed at a distance of 0.25 meter from the leading edge of the plate. So this is my leading edge of the plate. So at a distance of 0.25 meter on the plate, we see a boundary layer thickness of 1 mm. So we have to find out what will be the bound. So as we know that the boundary layer thickness will continuously grow as the edge of the plate here. So we have to find out what should be the value of the thickness of the boundary layer or the hydrodynamic boundary layer at a distance of 1 meter. Key concepts what we have going to use here. First, we learn about the local Reynolds number, how that's going to be important. And secondly, the Bloch's solution for laminar boundary layer. This is a very important one. Everybody learns about it over a flat plate with zero pressure gradient for estimation of boundary layer thickness. So we'll look into it. So this is a very important one in fluid mechanics. The fluid, let's look at schematic representation. Uh, the fluid approaches the plate with a free uniform free stream velocity, this infinity of 1 meter per second. This is given. At the plate surface, this right at the plate surface, no slip conditions apply. That means basically the fluid velocity at the surface is zero right here. Okay. Moving away from the surface, the velocity gradually increases. So as we move here, the velocity gradually increases and finally approaches the free stream velocity here. At this point, the velocity is zero right at the plate surface. So it's goes due to momentum diffusivity. There is a formation of this boundary layer. And so the velocity increases and finally it becomes equal to the free stream velocity. The region over which velocity change occurs, this region here, where this change in velocity occurs from 0 to the 99% of the free stream velocity is called the boundary layer. Okay, so this is the boundary layer. Just read any standard textbook. The boundary layer begins at the leading edge right here and becomes progressively thicker as the fluid. So, and this will come, as you can see, thicker as the fluid moves downstream. So as the fluid moves downstream here, so this boundary layer becomes thicker. This occurs because of the viscous effects, diffuse momentum from here further away from the plate surface. Okay. And this is x1 0.25 and this is x2 is equal to 1 meter. Let's quickly look at what is meant by zero pressure gradient. So basically, there's no gradient over here. So let's the P is the pressure outside the boundary layer. So we have seen. Okay. Uh, so this is a condition for normal Blasius growth of laminar boundary layer over flat plate here. So what really it means that the static pressure outside the boundary layer does not change along the plate here. So here, the static pressure outside the boundary layer does not change. Okay. So it doesn't really mean that the pressure is zero. It's just that the pressure gradient is zero. Okay. That's one of the conditions for the Blasius solution. Fluid outside the boundary layer moves with a constant free stream velocity u infinity. The boundary layer is neither accelerated nor decelerated. So this is for the external, let's say here, for the external inviscid flow. for the external invisible flow here, a constant pressure corresponds to a constant external velocity, and this is the free stream velocity. Therefore, the free stream flow is neither accelerated nor decelerated, so it moves at a constant velocity along the plate. Okay. The boundary layer development is governed mainly by a competition between the fluid inertia and the viscous moment diffusion. Please read any standard textbook. Next part is very easy. The Blussier solution is given here for steady laminar boundary layer over a flat plate with zero pressure gradient. This is the boundary layer thickness. This is given by this one. This is the local Reynolds number, which is defined as this one in terms of x, where x is the distance from the leading edge of the plate here. This is viscosity. This is density, and so we know mu over rho is the kinematic viscosity mu here. So this is what it is. So this infinity x stays here. So this is new. So we put this here. So we put this solution right here. So we put here, and this is the expression what we got. So these are all details are given over here. So one important thing to see is the boundary layer thickness from the leading edge of the plate here is proportional to the square root of the distance from the leading edge of the plate. That's what we see here. So this distance, or the thickness of the boundary layer, is proportional to the square root of the distance along from the leading edge of the plate. So this value at delta 1 at the value of 0.25 meter is given. So this one at 1 meter can easily be calculated, and that's equal to 2 mm. So that is basically the answer to this problem. Now let's look at the application of this problem in chemical engineering. In the boundary layer concept has importance well beyond the momentum transfer. In momentum transfer, viscosity causes momentum to diffuse away from the surface, producing a velocity boundary layer, which we will rightly see. Okay. Similarly, thermal diffusivity. Right on the flat plate, there could be, I'm sure there is momentum diffusivity, there will be thermal diffusivity. So there will be a thermal boundary layer. So similarly, thermal diffusivity causes heat to diffuse to the fluid, producing a thermal boundary layer. Similarly, molecular diffusivity causes a species to diffuse to the fluid, producing a concentration boundary layer. So on the flat plate, there could be a hydrodynamic boundary layer, there could be a thermal boundary layer, there could be a concentration boundary layer. And the relative thickness of that, of course, depends upon the Prandtl number in case of the thermal boundary layer, and of the Schmidt number in case of the concentration boundary layer. So we can compare it. Two, okay, and that of course gives rise to this Reynolds analogy. Again, please read any standard textbook. Um, so what are the applications here? For design of plate and frame heat exchangers, fluid flowing over a large flat vertical plate, in plate and frame heat exchangers, that's very popular in chemical process industries. So there's a fluid flowing over large flat vertical plates. So laminar or turbulent boundary layer data are used for calculating overall heat transfer coefficients. Very important. Again, using the Prandtl number. So that thing comes out depends upon the relative thickness of the hydrodynamic and the thermal boundary layer. Again, for heterogeneous catalysis, let's say fixed bed reactors, reactants must diffuse through laminar boundary layer to reach the catalyst wall. Thiele modulus and effectiveness factor, that's whether it's kinetically controlled or mass transfer control reaction, depends on the hydrodynamic boundary layer thickness and, of course, the concentration boundary layer thickness. Okay, so there are a lot of important applications of this boundary layer. What I would suggest that you read any standard textbook, and I'm sure please read your university and college lecture notes. So anyway, the answer to your problem is 2 mm.